All right, welcome back. We're having a look at some applications and applications of integration and how they might be used. So this really adds value, I think, to the whole process. All right, so I've got a rather complicated diagram here of a heart and all of the various bits and pieces that make up the heart. Now, we're not expected as the application of our mathematics to become experts in a particular field. What we're asked to do is to make sure that our maths is sound. Okay? So the cardiac output of a heart is a volume of blood per unit time. So it's the volume dV dt. The rate of flow into the aorta, which is a major component of the heart, and so it fills up all of those particular parts. You can see all the arteries going out, the arrows are there. Dye dilution is used to measure the cardiac output, which they're calling F. Dye is injected into the right atrium and probe injected into the aorta measures the concentration of dye over equal intervals of time till the dye is cleared out. At some point T, then the amount of dye which flows past the measuring point during the interval is a particular interval time. So we've got our T interval and our Ti minus 1. And then somewhere in there is our representative Ti. And we use the asterisk to denote all such Ti's. All right, so the volume times the volume times dV dt times time times mass dV, the mass per volume. We get some cancellations here. So we get the volumes are cancelling, that's 1 in disguise. We get the times cancelling, that's 1 in disguise. And so all we're left with, when we put these together, is the mass. And that is the force, or the flow, the amount, F, the amount of output, multiplied by the interval, times the concentration of the dye at the also represented intervals, and that represents our AI. So the total amount of dye would be approximated by the sum of all such AIs, which could be the sum of all such concentrations in time by that representative change in T. So our interval 0 to T so this represents our output towards T. So the amount of dye interval and the product of the concentration per unit time, and that is equal to 0 for the T interval so we can see that the interval is very helpful. And finally we get force is our A, remembering that was our A, divided by the integral, or the amount, I said force, but the amount is C T dt. So the application and use of integration to help in the amount of flow, F, that flows out, which is dependent on the total amount of time, the total amount of dye over the total amount of time is drawn together by a model. And that is a mathematical equation that has a model that is useful. Okay? So let's see if we can put some numbers to that and see if we can make that make sense. So the dilution method was used to model, there you go, that's a good thing that I said model, the cardiac output after 10 milligrams of dye was injected. The concentration of dye is modelled by this particular equation, which is a quadratic, where time is measured in seconds. Find the cardiac output F. Okay, so we've got our CT function as given in the question is 1/4 T 15 minus T. So what does that look like? Well, if we do the expansion, we'll get 15 on T, 15 on 4 T minus 1/4 T squared. So that's our CT function in a more regular quadratic form. So it's got two parts to it. And so we can go ahead and think about that. Now, if we were going to assign this to 0, okay, solving it in this form, you wouldn't change it to the other form. I just wanted to show you that it was a quadratic. We would leave it here, and it's equal to 0, and we say, when is this true? When is this true? Well, T, it's true when T is 0. T zeroes everything else out. T 0. It's true when the bracket is 0. When the bracket is 0, T would have to be 15. So we've got two T values now that are 0 and 15, and that represents the intercepts of this quadratic. So this quadratic looks like this. 0 and 15, and it has a function that's symmetrical, and CT. Alright, so our x-axis is a t-axis. So our interval is t15. The particular part that we want is the included part here. So we're going to integrate to 0 to 15 CT dt, which will be equal to the integral of 0 to 15 1/4 T 15 minus T dt. Now we'll expand like we did up here, so we'll get the integral 0 to 15, just putting the first term positive there and the second term negative there, t. And now we can go ahead and do the integration. So the integration will be up and under, so we'll get t squared divided by 2, so it'll be 15 t squared divided by 2. We already have a 4 there, so 4 times 2 is 8. Okay, so 4 times 2 will be 8. For the next one, t squared becomes t3 divided by 3, but we already have a 4 there, so make sure you don't eliminate them. Okay, now we're going to do that between 0 and 15, and we achieve that by the fundamental theorem of calculus. So we're going to put the scaffolding together, and it'll be quite a big scaffold because there's lots of parts to it. So 15 variable squared over 8 minus variable cubed over 12. Repeating, so that's the drudgery. 8 minus the cube over 8. And we're going to bomb this one with 15. And we're going to bomb all of this with 0. Now if we put 0 in, that's a polynomial of a type. Nothing to check. So we're only having to deal with 15 parts. Okay? Alright, so let's see what we can do. So 15 times 15 is 15 cubed. So I'm just going to put 15 cubed on 8. And we already had a 15 cubed on 12. Now what's common between 8 and 12? Probably 4. So we'll take the 15 cubed out the front. I know, it's a bit unusual, but we'll take the 15 cubed and the 4 out. And what would the first term be? It'd be a half, wouldn't it? And what would the second term be? It'd be a third. So it's just to simplify the adding of fractions. So, we've got to do this whole thing again. So we're going to end up with 15 cubed on 4 multiplied by 3/6 minus 2/6. So we're going to end up with 15 cubed over 4, 3 minus 2. I didn't need to do that, but I'm very generous. 15, 3 on 4. 3 minus 2 is 1/6 times. I've taken the bracket away. So we end up with 15 cubed. There could be factors there, so let's have a look with our calculator. Let's go for 15 cubed to the power 3 is a lot. Let's see if we can divide that by 4. No, so we'll times that by 4 and we'll divide that by 6 and see if 6 is a factor. Ooh, not really. Times by 6. Let's just clear all that away. 15 to the power 3. 3375. Divide by 4. No, I'm going to keep it going as 3375 over 24, but that's only part of the solution, because our model said that the flow was going to be a divided by the integral from 0 to t c t dt. Now we've done that, so it's 10 over 3375 divided by 24, which we can say is 10 divided by 3375 over 24, which is 10 times, so 240 over 3375. So let's have a look at that. I'm not liking that. Not liking that at all. So I'm just going to put this over here for a minute and have a look at this. Just going over this a little bit. Minus 2 is incorrect. I do 15 cubed. Divide that by 5. Do I get any luck? 675. So I'm thinking divided by 5 would be 675. 5. I'm going to leave that like that, and this one here, I'm going to say is 240 divided by 335. No, I'm just going to do it the long way. 10 divided by 3375 divided by 24. 1.23. Which approximates 0.24. 3, 4, 5, 6, 7, 8, 9. That's pretty funny. Have to have a couple of extra molds. One, 2 units. Okay. Alright, so let's have a think about that. And I think that's fairly involved, but you can see that when you're modelling and going through, you've got to double check, redo things, see if they all come out and make sense. And just checking a few things. So I might just think about this a little bit further. I'm a bit uncomfortable with this particular value here. It's probably okay, but I just want to explore it a bit more because I don't like this. I don't like these sums. So I'm just going to explore this a bit more and see if we get something different, just to see what my units will be like. So one of the things that I can do here is this thing here. I'll just bring this down here, and we can make it 15 cubed divided by factors of 4 are 2, factors of 6 are 2 and 3. I think we can do that. Now 15 cubed 15 cubed divided by 3. Let's just try this one. So 15 cubed divided by 3 gives me 1125. Now 1125, and it's divided by 2 2s are 4, 4 2s are 8. Now 1125 divided by 8, it's just that I'm trying to find a whole number, and I don't think there is one, so I'm just going for that one. So 1125, that's just a better number for my integral. So I'm just going to replace that with 1125 over 8, and so this becomes 1125 over 8. So 10 divided by 1125 over 8. And so I'll do that one, and let's see where we come out with that. I'll just probably do the same thing, but may not be. So 1125 divided by 8 is a decimal. Let's pop that into the memory. I'll just do 10 divided by 140. That's better. 0.071 repeater units. So that's the one I'm going to go with. Alright, so sometimes just simplifying in your model, looking for a better number. I just didn't like the size of these numbers, so splitting the denominator up into its factors, playing with its factors until I get something that I'm a bit more comfortable with. And then if you've got to do a big number, then you've got to do a big number. But essentially that's where that one lands. Alright, we'll come back and we'll have a look at another example of a model. Let's do that in a minute. Back soon.